I just love using the microphone so much. All right. For anyone who missed what I just said, who is watching outside, we're going to now start mixing AVX and OpenMP. All right, let's navigate my way to something useful. CD NCKU, yay. See, we are in the GPU class. You guys can see what I'm doing. Let's make a directory, mkdir for, we're doing AVX and OpenMP. If you guys aren't following me, start following me because you're going to copy what I'm writing here. So may the force be with you. Let's see. With these two includes, we're able to perform general computation, or STDO is a standard input-output. We've got OpenMP for our multi-core computations. If we want to use AVX, SIMD, vectorization, we need to include immintrin.h. If you're using SSE, that would be X, but we're using AVX, so we're looking for intrin.h. We also want to, because we're trying to copy this thing here, we're trying to break up the work that we perform on array A into 4 parts, 1 for each thread, and then we perform AVX computation on each of those parts. We need to declare A. It's going to have 32 pieces. So let's define a variable. Whoops. And we need to define the number of OpenMP threads. And we are ready to rock and roll. Where to start? Well, I know a good place to start. We need to allocate the memory for A. But because we're going to be packing, oh, I love this. All right. Because we're packing A into AVX type registers, we need to align it properly. We can't just use malloc to allocate memory. We can't allocate it on the stack. So we need to be careful about how we allocate memory for A. Oh, we also need to create a global pointer to A. If we don't create a global pointer, actually this still works just fine. But in the future where you write your own functions to use A, if it's not global, you're going to have to pass it through, which means you're going to need a pointer to a pointer. I'd rather avoid making things overly complicated. We're going to use POSIX memline. How do we use POSIX memline? That's the function. That is the first argument. Alignment. Alignment is a size type. I'll keep it 32 bits, sorry. N times size of float. Rocking and rolling. We've aligned it. As soon as you finish writing the code for POSIX memline, what's the second piece of code that you write? You free it, or I find where you live, and I pay you a visit during the Chinese New Year to make sure that you free future that you allocate on my server in the future. If we want to make sure that this works, we need to compile it. Let's see, we may as well start using all of the flags that we want straight away. O3 optimization, or at least O2 is required. We also need, better get used to putting the MAVX flag in. You guys can see that. Oh, hang on, let me clear the screen so you guys can better see what I'm doing. MAVX is the flag that you need to use for compiling it with AVX support. we need OpenMP support, so we chuck that in there. With level 2 and level 3 optimization, you'll tell the code that you're able to allow vectorization, which will make AVX possible. And it ran. I'm going to run it. It doesn't do anything else. I just want to make sure there are no segmentation faults or any problems occurring during my allocation. Now let's see. We need to set the values of A. Why do you think I set A to be equal to the floating point value of I? The reason is because we want to make sure that we have a way of debugging our code later. So we have an easy way of predicting what the values will be. Otherwise, when it comes time to testing, you're going to see that getting AVX working together with OpenMP can be quite fickle, can be quite difficult, and is downright impossible using the compiler alone. It will not run. It will just give you a seg fault, and it will fail completely. We're going to perform our calculation in this space here. We're going to multiply A by 2. And then after that, we need to check the answer. We're just going to need another for loop. I could have cut and pasted. Forget it. All right. Does anyone see any bugs? We're going to find out. Looks okay to me. Looks like the values of A are fine because we haven't done anything fancy yet. We're just setting up our problem. But now we want to multiply this array by 2, a scalar or vector multiplication. We want to use 4 OpenMP threads, and each OpenMP thread will have its own AVX register variable. Get it on. Let's do it. Let's see. I hate using this thing. Oh, I hate using that thing too. I'm a little bit skeptical. Yep. All right. I'm sorry for you guys who can't see over there. We have options, choices. We can do the AVX work first or the OpenMP work first. We have 2 layers of parallelization happening here. We're parallelizing across AVX and we're parallelizing across multiple OpenMP threads. We can create our OpenMP threads first, test to make sure they work first, then add AVX, or we can use AVX first, test to make sure AVX is working, then add OpenMP. Which do you think would be the better option? Which one, man? Tell me. Are you sick? I don't want to talk to you then. What do we reckon? Which one do we want to use first, AVX or OpenMP? Which one's easier? OpenMP. Sounds like a good place to start. You're absolutely right. OpenMP is the place to start here. Because OpenMP is easy. And there's not a lot of places we can go wrong. So let's do it. OpenMP parallelization. How many cores does this server have? 32 effective cores in the OpenMP environment variable. That's right. How many cores do I need? 4. If I don't set the number of OpenMP threads right now to the correct value, this whole experiment is going to fail dismally and very, very quickly, because we're going to see you're going to get a segfault if you're not careful here. Then we have pragmas. Remember that bracket must be down there. It can't be into the pragma. And here we are. Int TID equals OMP get thread number. Very first thing we're going to do is make each thread report back. Wonderful. and it works. So we can see we've created 4 threads. Now, just another heads up for you guys. In the Linux environment, in the Linux operating system, and in Windows too, we can force thread 0 to be managed by core 0, thread 1 to be managed by core 1, thread 2 to be managed by core 2, etc. We can actually lock the OpenMP threads into the relevant physical cores. This is by fixing the thread affinity. It is a good idea to do so in a Linux operating system. If you have a Linux server running a calculation, you want to make sure that the thread affinity is locked in such a way that the cores are locked to an OpenMP thread. If you do not do this, what happens is, in your computation, in most of our computations here, in this instance here, we only do one simple computation. We create our OpenMP threads and we do this one thing and that's it. But in most cores, our computations are quite complex. We do many computations. What you see happening in Linux and Windows is that the OpenMP threads are passed to different physical cores at different times during your calculation. This is a horrible, horrible idea because it actually takes time to swap control from one physical core over to another one. The best possible performance is going to be obtained by locking the threads in. It also can potentially make your system unstable. So I never said that it was the best outcome in terms of flexibility for your server, but for computational speed, we lock it in. In this case, we have 4 threads, which means we have 32 cores in our server. The reason why I haven't locked the threads in for this class is because all of you guys are using my server. If I lock the threads to physical cores, that means that in this class, if we create a code that uses 4 OpenMP threads, my server will only use the first 4 cores, and the rest will be unused. But by letting them float like this, I let you guys use my machine, and the 4 cores that this man uses are different to the 4 cores that that man uses. By doing this, we're able to share the computational load across the server. That's a great idea if you're doing more than one job or have more than one user, but if you want the fastest possible code to run in the fastest possible time, unplug the internet cable from the machine, boot all of the users, make sure the server is only doing one thing, your job, and then run it with locked threads. It's only possible if you can actually unplug the cable. So in this case, we haven't locked the threads to physical cores. Oh, now it's time. What do we need to do? Each thread is going to need its own AVX type variable. This AVX type variable will be private to each thread, which is why I'm going to declare it inside my parallel section. It's made private by default then. And each AVXA section is going to look at a different part. This one here is going to look here. 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 Now, look where exactly? This is a question. Because green sucks, red's all right. This one is pretty clearly going to start at 0. No question. This one here, this thread's going to control from 0 to 7. Does this one start at 8? It does not. Because the first thing we're going to do is transform A from an array of floating point variables into an array of AVX type variables. And since this thread here is only going to control 8 elements, that's one AVX type, this guy here is going to be looking at the index of this part, which has an index of 1, and that is 2, and that is 3. Complicated. Let's write the code for it. Let's see, we need to declare it first. So there is our declaration for our AVX type. We don't know what it's holding yet. I haven't told the computer what this AVX type is going to be holding. I haven't told it if it's going to hold 8 floats or 16 half precision integers or 4 doubles. But it doesn't matter because all we care about is the size. What actually happens depends on what functions we use. Let's see, we also want an AVX variable. Now, Why am I doing this? Remember, my mission here was to take this array and perform a scalar multiplication of this array by multiplying each element by 2. So right now it's 0, 1, 2, all the way up to 31. When I multiply it by 2, it will be 0, 2, 4, 6, 8. But all my operations are happening in AVX land. The number 2 is a scalar type. It's a scalar variable with 32 bits. We need an AVX variable that has 2 in every part. So we need to use a special function for that. So I've called it AVX2 so that you guys know that it is an AVX equivalent of the constant 2. And we need a special function for that. Whoops. I believe that's it. 1 underscore, man. All AVX functions use 1 underscore. And set 1, which means we're setting every part of our AVX register, all 8 elements, to 1. P means in parallel. S is single precision, which means we're creating 8 of them. If we had 4 double precision variables, it would be PD at the end instead of PS. Now, we're almost there. But before I do anything, people, I'm going to save it and compile it. Oh, what am I missing here? Is it what's wrong? Can you guys see the bug? The notes are online. You can see on your notes. Look back to last week. M. There are too many M's. We're done. There were too many M's there. It wasn't MM. It was just M. We haven't done anything yet, so the answer is still fine. The good news is we haven't produced any reason for it to have a segfault yet, but we're going to right now. Now AVXA needs to be set. Now AVXA is an array. I make it an array because, remember, in this case, 什么有错，我们只有一个 AVX element，因为我们只有处理8个东西。We only need to address the computation of 8 floating point elements. So we only require 1 AVX type register. But if this is longer, we're going to need multiple components inside our AVXA. It's going to need to be an array of AVX types. So I set it to be an array by putting this star here, which means that, well, you're going to see what it means very, very soon. When we use it, we're going to need to treat it like an array. But we need to map it to A somehow. We're going to use the same trick that we used last week. Remember last week we used a force type convention to change it from a float to an AVX type. But then we also need to move the index. It is changing A from A to a floating point AVX type array plus an index. Now that index, we talked about this just before. This guy is going to not look at the 8th element or the 9th element, number 8. It has to look at 1. This one will be looking at 2, this one will be looking at 3, which means at the moment our index is just the thread ID. Once we've got this, then we're cooking with gas. We can perform our computation. Now, if this was a vector that contained 64 elements, each AVX would need to perform, we'd need to perform 2 AVX computations in each loop. So I would then have to put a for loop in here to take into account each part that I needed to do. But I don't need a for loop here because each AVX computation only looks at 1 part because we only have 32 elements in our array and 4 OpenMP threads. So it's just right. So that means instead of using a for loop, I just need to write it down. Now, AVXA. Remember, this is an array, so we need to refer to the 0th one. I refer to 0 here with good reason. Because, remember, each OpenMP thread, has its own AVXA. If I were to make AVXA a shared variable and widely available, that would mean that I would need to adjust which part of AVX each thread was looking at. I'm avoiding this problem by making AVX private, which is a good idea. It's much safer. And we want to multiply these things together. It is a multiplication which is occurring in parallel. Well, what are we multiplying? AVXA and AVX2. And that is it, my little chickadees. We can compile this and it should work just fine. Once I've done this, we should be able to see that when we print this array out, that value A, all of the elements inside A have been doubled. So we can see that we've done two things here. We've only created 4 threads. So each one of these threads is going to perform a single AVX type operation, and each time we call this AVX intrinsic function, we're performing floating point computations across 8 variables. So the potential speed up for this code, the theoretical speed up for this code is 4 hours. What's the theoretical speed up for this code? 4 times, because we're using OpenMP, and each cycle we're processing 8 floats instead of 1. So 4 times 8 is 32. The theoretical parallel speed up for this code is 32 times. So it is very, very efficient code, considering that we only create 4 OpenMP threads. If I were to go crazy and use all 32 cores on my machine, we can actually process quite a large size of data by using AVX intrinsic computation like this. All right. Does it work? Beats me, man. We're going to find out. It compiled. Did it work? Yes, it did. We managed to double every element all the way down to this. So, what I want you guys to do, I'll put this is the real meat of my code. Make sure you get your code working. I want everyone to log in, write this code, get it compiled and running. Then I want you guys to start playing around with it. I want to see if you can crash it. I want to see what happens when you use malloc instead of POSIX memberline. I want you to see what happens when you change the alignment variable from 32 to 8 or to 64. I want to see what happens if we change the index here. There are at least 30 ways that you can make this code stop working. By some miracle, I've managed to show you the correct way straight away, but there are many ways that it can fail. So I want you guys to finish writing this code down, and I want you guys to start experimenting to see if you can make it crash. Do it. Man, you are way Okay, by now almost all of you should have finished the problem, the challenge that I gave you to solve. All of you have succeeded in using multiple AVX computations in each OpenMP course. Many of you have also discovered that if you try to use malloc instead of POSIX memberlined, it will never work. It is impossible to succeed because by using OpenMP together with AVX, and O3 flag, we're asking the computer to do a lot of work very quickly. The computer will not check to make sure that its cache grabs were accurate and complete, and you will get seg faults because the computer will inadvertently grab the wrong section of memory from its banks. So you must use POSIX memberline, otherwise this whole thing falls apart. In your own time, I want you guys to try to use object dump, OBJDUMP, to deconstruct the compiled code objects to see how it works. I want you guys to make sure that you are using AVX. In this case, we know we've used AVX because otherwise this example would not have succeeded. If our AVX wasn't working properly, we could not have completed this example because if we were using SSE instead of AVX, only half of this array would have been computed. So this is a reason why we use this code. This code proves that AVX works. Try to use the compiler to automatically vectorize this. So go into your codes. Because we're using OpenMP, we can use a OpenMP parallel for loop if we want. Don't use AVX intrinsic functions. See if you can use MAVX and -03 to get the computer to automatically compile your code to use OpenMP and AVX at the same time. You might remember that last week when we tried to force the compiler to create AVX code, it failed, and it created bad SSE code. The same thing happens, or worse things happen if you try to do it with OpenMP. If you ask the OpenMP compiler to try to compile your code into an executable that uses AVX at the same time, not only will it not use AVX, but it will also create segmentation faults, even though you used POSIX memberline. So with the most recent Intel compiler, my knowledge is the Intel compiler doesn't work. The Intel compiler is not capable of using AVX or SSE together with OpenMP. It will produce seg faults. So sometimes when you're using compilers to do the automatic vectorization, your code will crash, but it won't be your fault. It will be because of compiler bugs. And they still exist, unfortunately. So we know the concept. Today we took our N elements and we broke it down into AVX types, and then we shared the AVX types. In this case, we used one OpenMP thread, to hold one AVX type. Once we changed N from 32 to 64, we asked each OpenMP thread to hold 2 of them. So by doing this kind of thing, you're able to ask your code to actually manage an arbitrarily sized piece of work. But we do have to be careful. We have to make sure that this number here, this is 32 here, we can evenly divide it by 4 times 8. If it doesn't evenly divide, even if you try to use compiler to auto-vectorize, it will give you a seg fault. If this number is not easily divided by 8 times your number of cores, you will get a seg fault every time. So, moral of the story is, if you're using the compiler to try to help you parallelize automatically, this number needs to be divisible by 8p, where p is your number of threads. If you're writing the code yourself with intrinsic functions, this array needs to be divisible by 8p. If your code is not divisible by 8p, and you're asking the compiler to try to do vectorization together with OpenMP, you will get a seg fault and it will fail. So we normally pad our arrays to make sure they are complete divisors of 8p. So in this case, we have 4 threads, 8 AVX elements per thread, or 8 floating points per AVX float. We need to make sure we can easily divide this by, 8 really, just to make sure, or 32. Which is why we always use arrays of length 32, or easily dividable by 32. Let's see. Yeah, unfortunately, if n is not easily divisible by 8p, it must be padded. The compilers do not know how to pad them. Or I should say, the current Intel compilers to this date do not successfully pad them to the correct length. Intel calls this a feature and not a bug. It is a bug. Be careful. If you can, choose your problem size. Here's a code that we just wrote. Oh no, this is a different code. This is a code that uses SHLL to solve the shallow water equations using OpenMP and AVX. I'm actually going to talk a little bit more about this example because the method that we've stumbled onto here, using OpenMP together with AVX parallelization, theoretically gives you a very large performance increase. So 32 physical cores times 8. 32 times 8, that's 200 something speed up. That is actually more powerful than a GPU, which is why so many people at parallel computing conferences get antsy when people present GPU speed ups of larger than 50. Because as a matter of fact, any computing system which is correctly using AVX together with OpenMP should theoretically be able to match the performance of a GPU. Because the CPU is an extremely powerful device. The only reason people get away with reporting incredibly large speedups is because the compilers fail to vectorize. So most of the time when people write OpenMP code, even when they're using level 3 optimization, the codes, well, we proved last week the codes do not use AVX. The auto vectorization on level 3 optimization uses SSE, and it sucks. We also looked at the quality of the deconstructed machine code. If you remember, we used object dump, deconstructed it, and we saw that it was bad. Much, much larger than our own code. So any well-written CPU code will be a match. I'm going to show you some of that today. There's the code we wrote today. Application time. I have two applications to show you today. One is a flash flooding of a city environment. That's like a tsunami in a city. The other one is a 3D heat transfer. 3D heat transfer, man, is it's a piece of cake. I didn't ask you to do it. Here's the equations. You've seen the equations before. We're using FTCS in 3D, which means we've got the old temperatures, sorry, the new temperature is the old one plus that and that in X, Y, Z. Nothing tricky here. These are the coefficients, constants. dt doesn't change, theta doesn't change, dx, dy, dz doesn't change. So these are constants which we can set in AVX using set 1. Here's my problem. It is a CPU fan. It is, a heat sink with fins. So I'm going to perform a heat transfer analysis on this. I'm going to use 64 by 64 by 64. That's 250,000 cells. Take 200,000 time steps. Blah, 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 blah. First of all, we start with what we know. OpenMP is the easiest code to get off the ground. So whenever we do any problem, just like we did today with this thing, we start with OpenMP, get OpenMP working, and then we insert AVX later. The results look like this. We know the results from this problem. It's a piece of cake. So it's not difficult. Code, code, code. In this case, what is the biggest problem with using AVX? Remember, AVX is SIMD vectorization. That means every cell must perform every computation, and we can't perform if computations on each individual element in our problem, because every AVX computation performs computations across 8 elements. We can't use if on each one. If we were to try to use if on each of the 8 elements, we would need to use what we call masks, AVX or vector masks. These are not nice things to do, but you can learn about masks by going to the Intel Intrinsics page. But if we want to avoid that, we need to create extra memory to hold the neighboring temperature values. So this problem, theoretically, we only need to create one array to hold the temperature values, but this time I'm going to create 7 variables which hold temperatures. One, A, which holds the temperature at the center, and the next ones hold the temperatures left, right, up, down. So we've increased the memory by 6 times. But we're going to be increasing the performance by 8 times. So we're basically spending memory to get an increased performance. Is it worth doing? Probably, because memory is cheaper now than the computational capacity that we can afford to use. So, basically when we write this code, there are several things I need to show here. One, any heat transfer code that uses FTCS finite differences of second order accuracy in time and first order accuracy in space needs to make sure that each of those coefficients has a value of less than 0.5. in which case in this case it's a 3D simulation, so we need to make sure that all of these three are less than 0.5. 还有一些学生有问我怎么用电脑算我的 code 跑得多快 It's here. We do not use the number of cycles per second when we measure time for computation, ever, because you're going to see that doesn't work because OpenMP is going to count the flops performed by your multiple cores, which means that you're going to get the wrong answer. What we need to do is look at the wall clock. The wall clock is the time, what the actual time is, and that is performed using the get time of day function. This is actually the time right now. Doesn't matter how many cores we have, it doesn't matter about any, it doesn't even matter if this is not the correct time, because I know that on a server, half the time we can't be bothered setting the correct date. In most Linux machines now, it automatically goes to a server and gets the correct time and date. We can control that, but in this case, we're getting the clock, the wall time, the actual time, and we transform it. So we've got the time here, we've got the time here, and we calculate the difference. We never use flops per cycle or seconds per flops or flops per second or any of these variables because that's not going to work if we're using OpenMP. In this code, we use POSIX memline. You guys know why we use POSIX memline now. 如果你没有用 POSIX memline 的话, you will get segmentation faults. It will not be your fault. 你写的 code 是100%是漂亮的，是对的，但是如果你用 malloc, you will get segmentation faults. If you use CUDA malloc, you will not. CUDA malloc actually goes to efforts to align data in memory. Because aligned data in memory means more efficient fetching from cache, or more efficient delivery to cache, I should say, and increases the performance. So CUDA knows what it's doing, but malloc is reckless. So all of our codes now use POSIX memline. My advice to you guys, if you're doing research and using codes, use POSIX memline, don't use malloc. We collect data. This is boring. Here is our OpenMP parallelization section. This is a transient computation. This is a nested loop parallelization. We've talked about this before. When we have nested loop parallelization, we must put our OpenMP thread creation outside the outermost loop. We cannot create and destroy OpenMP threads repeatedly inside our computation because OpenMP thread creation takes excessive amounts of time. It is probably easily the slowest part of this code. 最慢的这个 code 最慢的快，不是那个计算快，是这个东西 creating the parallel threads. If we create these threads inside our time loop, it will slow our code down by about 3,000%. It will make it blow up. So you cannot create threads inside a for loop. If you're going to use parallel computation, we create threads once and destroy them once, at the beginning and at the end. MPI is another tool for distributed memory computing. It is designed to do this by default because this is the way. But in OpenMP, we always choose to create them early. We create our threads outside our transient loop. It doesn't mean we can parallelize time, so we have to be careful. That's why we have barriers here. And then inside here, if we're just using OpenMP by itself, we can use Pragma OMP4. We cannot use Pragma OMP4 if we're using AVX. You guys probably have realized this. If we're using AVX together with OpenMP, we cannot use OpenMP4 because we need to control which part of our arrays are being performed by whom and what they're doing precisely. We can't allow OpenMP to automatically parallelize this anymore, which is why I taught you guys how to manually engage in OpenMP parallelization before I taught you the automatic treatment. Boring. You guys can read this anytime. Yep. If we want to make this go faster, even faster than it already is, we need to use AVX intrinsics. There are two parts. In this code, the first part of our computation checks to see what the temperature of the neighbor cells are. Because it is an explicit solution to a partial differential equation, we need to look left, right, up, down, back, and front. We need to know what the neighbors are. We can't use AVX to parallelize these if statements easily. We can't. And no compiler is smart enough to do it automatically. But the final computation phase, where we take our temperature values and apply them, every cell has the same computation applied. There are no if statements, which means we can use AVX to accelerate it. Here we use set 1PS to set our phi x, phi y, phi z values. Here is our beast. You can see here I haven't taken any chances. This code doesn't have any locally declared variables. I haven't created any local variables with local scope. I've declared everything outside and then explicitly made them shared or private. Actually, there's no reason to do this. If you've got a private variable, you can declare it inside. There's only one reason you can't. Winiman, is this C or C++? It is C. C++ allows you to create new variables with that new scope. C, on the other hand, is going to be a lot fussier. Traditional C, every variable must be created, defined at the beginning of the function. In normal C, not ISO C, before the ISO regulations were changed for C, you had to declare all of the parameters before you use them at the top. You can't introduce a variable, then perform some computational variable, some computation, and then introduce a new one using traditional C. C++ you can. C++ you can write int TID any way you like. So the code I just wrote for you guys was C++. And the code that you just wrote now using AVX was C++, but this is C. If you want to change to C++, all of these private variables you can declare right here. Just chuck their declarations here. They are automatically private. And everything else is automatically shared. So in fact, you don't have to go to this effort. This is our heat transfer computation. You can see in our heat transfer computation we have 3 derivatives to approximate. Second derivative in x, second derivative in y, second derivative in c. Here are the steps. Here are computations. You can see here every part of the calculation is broken down. So we actually have to think about what we're doing now. We can't just randomly multiply and add variables together. We actually need to consider the order of computation and perform them exactly. And by doing so, we get the maximum degree of performance, and each of these performs operations on 8 floating point variables. So each step is 8 computations, not 1. So by doing this, we're making sure that our ALU is burning, is on fire. We are loading our CPU to the maximum possible extent. If you do not do this and you turn off your vectorization, remember that ALU will only be using 1/8 of its capacity. It will only use one of its AVX registers each cycle. It won't use the full width. The speed up. This code, without any optimization, just using G++ to compile and run it, took 2,000 seconds to run. After I used OpenMP with 16 cores, with AVX, I got that down to 47 seconds. It's a bit faster. You can see why we invest time into this. This was a simple code, so it's a play toy. This is not going to be used in valid research, but the methods that I've shown you here are able to deliver you significant speed up. That could easily have been 20,000 seconds. 20,000 seconds changed to 400 seconds is a substantial increase in computational performance. That makes it worth your while. Keep in mind that that kind of performance is impossible to obtain with current compilers. So unfortunately for us, we are forced to manually perform most of the parallelization work. Yeah, good luck. So I also mentioned urban flash flooding. Last week and the week before and several other weeks, we've been solving the open surface shallow water equations, which are the height averaged Navier-Stokes equations for an incompressible flow, basically describing how water would flow on a floor. In this case, we have 3 buildings, and I'm flooding the city, and I want to compute how the water moves through that city. It is an important calculation. In Australia, where we don't have a lot of water, and when water comes, it's a big problem, but Taiwan, not important because there's water here every day, everywhere, and the drainage in this country is actually quite phenomenal. I've only seen Kaohsiung City flood once, and that was during a world record-breaking rain event. So it was phenomenal, but this happens in Australia all the time, flash flooding. In this case, I used AVX with OpenMP computing, so I needed to use AVX intrinsic functions to compute my split fluxes. Once I had all my split fluxes computed, I was able to update the state quickly. In this instance, I used 10 physical cores on my current machine. The speed up ranged from 36 times to 57 times, depending on my parameters for compilation. So we are going pretty quick. We've managed to accelerate the codes to a point where you're able to start competing with the GPU code. A Titan is going to give you a speed up of about 60 times for this. So theoretically speaking, if you're willing to go to the effort of writing a code which uses OpenMP together with AVX intrinsics, and it is hard, it is a lot of effort for a simple calculation, understandably, because this code here that we just wrote, if we didn't want to use AVX, that's our code. But if we want to make this go as fast as we can, we use OpenMP parallelization, and then we use AVX parallel registers again to break down the parallelization even further. It increases the size of your code by about 20 times, but you do get an incredible degree of speed up. And as you guys are aware, the reason that I'm teaching you is because every time I go to an international conference, researchers ask me, how can I be sure that my GPU code speed up is actually what it is? How can I be sure that my CPU code is as fast as it can be? By using OpenMP together with manual AVX intrinsics, your code is as fast as it can be. And you can confirm this by doing the deconstruction of your compiled objects and checking the machine code directly. It is a lot of effort to go through, but the rewards can be substantial. So, what's the moral of the story? Actually, we're at the last class of the course. This is the last lecture. After this, next week, you've got an exam. My personal preference, GPU codes are easier to write and provide a valuable return. So you can provide a 60 times speed up with a GTX Titan on any practical engineering problem, and the code is going to be quite simple to write, much simpler than this AVX OpenMP code. But if you're going to try to report the speed up to an international audience or write a research paper, and you tell the user or the reader that your speed up is 100 times, you're going to need to be able to justify by examining the CPU performance. There are two ways you can do. One is that you can disable all optimization and disable all parallelization on the system and use that as a benchmark. The other is to try to get your maximum performance out of your CPU system by using OpenMP together with AVX. Your call on what to do. I can tell you which ones I do. I have to do both. It's my responsibility. But don't be reckless when you're reporting GPU speed up. If you're going to report how fast your codes are in comparison to CPUs, you should be careful, because modern CPUs, especially the modern Skylake X's, which have AVX 512, which are able to compute 16 floating point elements per cycle in the ALU instead of the 8 we talk about here, they are powerful machines. Be careful. Today's prac. There is no prac. Haha. There's no prac today. You guys, I believe, have an assignment to hand in soon, and I'm pretty sure you guys have got your hands full for that. You can also prepare for next week's test. Next week's test. Let me tell you what's on it. Questions. Here's the kicker. This is a part that you guys are going to be very happy about or devastated. Next week's test is a closed book exam. You will not be able to bring in any material. I just want you, your brain, a pen and pencil, a calculator. I do not want you to go online. You will not be able to look at resources. You will not be able to look at PDFs. You will not be able to go onto the server. So the computer will be shut next Tuesday night. I'll be pulling the power plug out, And any students who have jobs running on it, they're going to lose them. Next week's exam will be a pen and paper exam. Not on the computers, no. So it's going to be in this room, but the computers will be off. You will not be connecting to my server or any server. Every code that you write will be on the paper from your own brain. Now, what does this mean? It means that if you make a syntax error, I'm not going to kill you. But if you make a mistake in the logical treatment of some degree of parallelization, then I will execute you. But syntax errors, I'll be nice about. You can relax about that. Your test will have 4 parts: OpenMP, SIMD vectorization, that is SSE and AVX. GPU, I'm still testing GPU, you're not free of GPU yet. And finally, numerical analysis topics. You guys have all had extensive practice at solving several PDEs in this course, plus several regression computations. In addition to those, you've had a wide range of filter experiences. You guys have learned numerical computations across a variety of activities, which we covered during classwork and tutorials. 20% of the exam will be covering questions on that. You'll need to use your calculator to solve it. If you forget to bring your calculator to next week's exam, you're probably studying the wrong degree. Engineers carry calculators with them all the time. Don't forget your calculator. Since you'll be doing calculations by hand, bring it. You guys ready? You'll be writing codes by hand on paper. If you think that sucks, I have to read your codes without a computer. It's going to kill me more than it kills you, I promise you that. I'm going to give you codes. You're going to have to debug them, find where they're broken. They will be easier than the mid-semester exam, because in the mid-semester exam you had help from a computer for your debugging. This time you don't, so it will be a little easier. I will ask you to perform some calculations by hand on problems that we have covered in class. And I might ask you to discuss aspects of parallel computing. I might give you a question that you have to answer. Now, 实这样的话, you can use Chinese if you need to. So you can use Chinese to write down your answer. I'll have to read your Chinese then, which is about as much fun as me reading your codes. It is pretty much the same kind of work to me. We'll see how we go. Some of the final exams you find on my website are actually closed book final exams. So they are still useful to look at. In this course history, about half of my final exams are open. Normally what happens is if my mid-semester exam is closed book, my end of semester is open. If my mid-semester is open, the end of semester is closed. I don't normally make them both closed or both open. Also, because it's closed book, I can't give you anything truly evil. I can only really test you on things that you've already seen. But that's still pretty bloody evil, because in this course you've seen a lot of stuff. I've asked you to perform computations in parallel across a wide range of engineering applications and mathematics applications. Anything in your assignment is also fair game. I could ask you a BiCG question, because everyone here is doing BiCG right now on GPU. And by the time your exam comes next week, everyone in this classroom is going to be an expert at BiCG on CPU, because you will have just spent the last 30, 40, 60 hours working on it before my test. So, be ready. If you have any questions, you can come see me anytime. I'll be in my office pretty much every day until then. Are there any questions before I let you go? No questions. The bus is leaving. Okay, knock yourselves out, people. You can work on your assignments. You can practice your AVX with OpenMP if you like. Yeah. Never.